Electrolysis. These are the learning outcomes of electrolysis. Describe electrolysis as the conduction of electricity by an ionic compound when molten or dissolved in water, leading to the decomposition of the electrolyte. Describe electrolysis as evidence for the existence of ions, which are held in a lattice when solid but which are free to move when molten or in solution. Describe in terms of the mobility of ions present and the electrode products. Predict the likely products of the electrolysis of a molten compound. Apply the idea of selective discharge. Predict the likely products of electrolysis of aqueous electrolyte. Construct equations for the reactions occurring at each electrode. Describe the electrolysis of purified aluminium oxide. Describe the electrolysis of aqueous copper 2 sulfate with copper electrodes. Describe electroplating of metals and describe the production of electrical energy from simple cells. So these are the learning outcomes. First of all, electrolysis. Electrolysis is the process by which ionic substances are decomposed or broken down into simpler substances when an electric current is passed through them. So remember, ionic substances should be in molten or in aqueous state. Only then they can decompose into its simpler ions when electricity is passed through it. Electricity, as we know, it's a flow of electrons or ions. And the condition is for electrolysis to work, the compound must contain ions. That means it should be an ionic compound. Covalent compounds cannot act as electrolytes because they contain neutral atoms. They do not contain ions. So this electrolysis works only for ionic compounds, and also they should be in molten or aqueous state. This is the setup of an electrolytic cell, an apparatus. So there will be an electrolyte. As I said before, it should be an aqueous or molten ionic compound. And then there are two rods called electrodes, anode and cathode. An anode is connected to the positive pole of the battery. Cathode is connected to the negative pole of the battery. So anode is positive and cathode is negative. And you can see, since anode is positive, anions attract towards the anode. Anions are negatively charged ions. A negatively charged ion is an anion. So that is attracted towards the anode, which is positive. Likewise, cations attract towards the cathode. Cations are positively charged ions. They attract towards the cathode. So this is what happens when the electricity is passed through the electrolyte. The ions must be free to move, which is possible when an ionic substance is dissolved in water or it is melted. For example, if electricity is passed through molten lead bromide, the lead bromide is broken down to form lead and bromine. So we can see what is happening during electrolysis. I showed you in the diagram above. Positively charged ions move to the negative electrode during electrolysis. They receive electrons and are reduced. So negative electrode is a cathode. So reduction happens at the cathode. Similarly, negatively charged ions move to the positive electrode during electrolysis. They lose electrons and are oxidized. So at the anode you can see oxidation. The substance that is broken down is called the electrolyte. Now we'll go through the examples. First of all, let's see for the molten salts. As we know, substances when molten or dissolved in aqueous media, they conduct electricity. So example is lead bromide. Place solid lead to bromide in a crucible and heat until it melts. Insert two carbon electrodes into the molten electrolyte and pass a direct current between them. Carbon electrodes are chosen because they have a high melting point and are inert. Inert means they will not react with the reactants and products during electrolysis. That's why we have selected it as the carbon electrodes. And what do you observe? You observe, the observations are, at the anode you can see bubbles of brown gas. That means that you can see lead bromide is being dissociated and bromine gas. Explanation, you will see the bromine vapor is being produced. Cathode observation is silvery liquid metal present at this electrode underneath the remaining molten electrolyte, which is the lead. So these are the observations, and you will come to know what is produced at each electrode. This is a diagram showing electrolysis of molten lead bromide. As you can see, lead ions and bromide ions are there. Lead ion, since it is cation, it moves towards the cathode, which is negative. And Br minus, since it is negative anion, it moves towards the anode and forms their bromine vapor. Lead ions will get deposited at the cathode. So at the cathode you will see lead ions undergo reduction, gains electrons and form lead. At the anode, bromide ions loses electrons and forms bromine. That's what happens during the electrolysis of molten lead bromide. So the reaction, as I mentioned above, you can see the reactions. At the anode, what's happening? At the cathode, what's happening? Anode, bromide loses electron. Loss of electron is oxidation at the anode. So you can see oxidation happens and you will get Br2. Similarly, at the cathode, you will see reduction. So lead ions gains electrons and form lead. So this is the electrolysis of molten lead to bromide. It is easy to predict the products of electrolysis of molten electrolytes because they simply split into their elements. The metal is formed at the negative electrode because that is where the positive metal ions are attracted. And the nonmetal is formed at the positive electrode where the negative nonmetal ions are attracted. What are the products obtained at cathode and anode when the following electrolytes undergo electrolysis? You can write it and see what's the answer you are getting. Zinc chloride and aluminium oxide. Pause the video and write your own answers. So this is how: zinc chloride at anode, chlorine; at the cathode, zinc. Aluminium oxide at anode, oxygen; at the cathode, aluminium. So metals forms at the cathode, non-metals forms at the anode. That's how. And the equations are shown here. Zinc chloride at cathode, reduction happens. Zinc ions gains electrons and form zinc. At the anode, oxidation happens. So chloride ions loses electrons and forms chlorine. Similarly for aluminium oxide, at the anode, oxide ions loses electrons and form oxygen. Cathode gains electrons. Aluminium gains electrons and form aluminium. So aluminium ions gains electrons and forms aluminium. So always remember, at the anode always oxidation, at the cathode always reduction. Next we can see electrolysis of ionic solutions. Solutions means it is in aqueous media. So this will be little more complicated than molten because you will see more ions from water also. Water molecules can provide hydrogen ions, H+ ions and hydroxide ions, OH- ions, in addition to the ions from the ionic compounds. So at the negative electrode, you can see metal ions and hydrogen ions are positively charged. Whether you get the metal or the hydrogen during electrolysis depends on the position of the metal in the reactivity series. The metal will be produced if it is less reactive than hydrogen. Hydrogen will be produced if the metal is more reactive than hydrogen. So this is a reactivity series of the metals which you can use it for determining which is more reactive and which is least reactive. potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, copper, silver, gold, platinum. So this is the series, and you can remember the series by taking this mnemonics also. Use this for the easy way to remember. Please stop calling me a careless zebra. Instead, try learning how copper saves gold. You can use this. So from the series, we can understand that if there is hydrogen and a metal above that, obviously hydrogen is least reactive, so hydrogen will move towards the respective electrodes and it gets discharged soon. If the metal is below hydrogen in the reactivity series, then only the metal ions will get discharged easily than hydrogen. So this is the series which you have to remember. Now at anode, what happens? Anode, you can see negative ions will be attracted to the positive electrode and it gets oxidized. So either OH minus or nonmetal ions will lose electrons and oxygen gas or the gas of the nonmetal in question is released. So this also depends on the preferential discharge. And there is an order for the discharge of anions. Less easily discharged is sulfate, nitrate, and it increases towards the right side: chloride, bromide, iodide, hydroxide. So when hydroxide comes, it becomes more easily discharged. If hydroxide and sulfate is present, then obviously hydroxide will move and gets easily discharged than sulfate ion. Therefore, at the anode, oxygen gas will be produced unless the ionic compound contains halide ions, in which case halogen will be produced. That is the case only for the concentrated solutions. Otherwise, you can follow this rule. Only if the solution is concentrated halide solutions, then we can see the different rule. We have to follow the different rule. So let's see an example: electrolysis of dilute sodium chloride solution. So we know that here ions present will be from sodium chloride and also from water. So at the anode, what happens? Anions, you have got two anions here, OH minus and Cl minus. But as we know, it is dilute, it's not concentrated. So OH minus ions, according to our table, it's less reactive, so it gets easily discharged, forming gas bubbles. And how do you test the gas bubbles? When OH minus comes, we know oxygen gas has been produced. You can test it to confirm. Bring a glowing splint towards a gas, it relights, so that it's confirmed that the gas produced was oxygen. And the equation is 4OH minus gives 2H2O plus O2 plus 4 electron. So electron is being released. That means anode undergoes oxidation always. What happens at the cathode? We have two cations here, H plus ion and Na plus ion. But as we know from the reactivity series, H plus ion is coming below the reactivity series than sodium. So H plus ion is selectively discharged to form hydrogen gas through the process of reduction. So since hydrogen gas has been produced, you can see the gas bubbles. How will you test the gas? You know it's hydrogen, so to confirm, you test it with a lighted splint. Bring a lighted splint and you can hear a pop sound, so that it's confirmed that it's hydrogen gas. So that's how the electrolysis happens for dilute sodium chloride solution. Another example is we are going to electrolyze concentrated sodium chloride. So now it's concentrated. That means halide ions is more than hydroxide ions. That's the only change you have to notice here. For the cathode, no problem at all, because sodium and hydrogen ions will be there. And obviously, sodium is above the reactivity series, hydrogen is below the reactivity series. So hydrogen ions get discharged soon to form hydrogen gas. This is as similar to the dilute solution, but when it's concentrated, the halide ions, the negative ions, anions, is more than hydroxide ions. So the preferential discharge will be for chloride ion. Since it is more in number, it's concentrated, it moves readily to the electrode and it gets discharged soon by the process of oxidation. So Cl minus undergoes oxidation to form Cl2 and you will see the chlorine gas. And what is left behind as an electrolyte? Since hydrogen is gone and Cl is gone, the left behind is sodium ion and hydroxide ions. So they both combine and can form sodium hydroxide solution. So the resultant solution will be alkaline in nature. So this is how the electrolysis of concentrated sodium chloride solution happens. And another name for concentrated sodium chloride solution is brine. So if the question is brine solution, also do the same. Next example is electrolysis of dilute sulfuric acid. Here also it's dilute, so the ions present will be H plus and OH minus from water and H plus and sulfate ions from sulfuric acid. As you can see, since only positive ion present is H plus ion, there is no confusion. H plus ions undergoes reduction and forms H2 at the cathode. And what happens at the anode? You have two ions here, OH minus ion and sulfate ions. As we know, OH minus ions is readily to discharge. It's ready to discharge soon, so easily discharged. Selective discharge happens for OH minus ions and forms oxygen gas. So you will see hydrogen gas at the cathode and oxygen gas at the anode. The production of hydrogen gas will be twice that of oxygen gas. So that's about electrolysis of sulfuric acid. Next we will see electrolysis of aqueous copper sulfate using inert electrodes. We select inert electrode as carbon. So here this electrolyte is copper 2 sulfate solution. So the ions present will be copper 2 plus ion, sulfate 2 minus ion, and then since the solution is aqueous, you get the ions from water H plus and OH minus also. And here when you consider cathode, you have here two ions, copper ions and hydrogen ions. Again with reference to the reactivity series, copper ions comes below the hydrogen ions. So copper ions is preferentially discharged and gets reduced and form copper. So you will see either a brown deposit or a pink deposit of copper at the cathode. And what happens at the anode? Anode you have here OH minus ion and sulfate ions. So for sure OH minus will be preferentially discharged and produces oxygen and water. So since copper sulfate is being dissociated and since copper ions is been moving away, we can see that the blue color of the original blue color solution, copper sulfate was blue in color, that solution, the color of the solution fades. As time passes, the blue color decolorizes because copper ions is being discharged. So the ultimate observation is the blue color of the solution decolorizes and you will see the pink solid or brown deposit of copper at the cathode. And you will see the bubbles given off at the anode. These are the observations of aqueous copper sulfate using inert electrodes or carbon electrodes or graphite electrodes. Now let's see an example of aqueous copper sulfate using copper electrodes. What happens if you use copper electrodes? Copper sulfate solution contains same ions, copper ion, sulfate ion, hydrogen ion and OH minus ions from water. So at the cathode, copper ions are preferentially discharged because copper ions comes below hydrogen in the reactivity series. And it undergoes reduction and you will see the deposit of copper. At the anode, what happens? Here the electrodes are not inert. Here we are using copper electrodes as a cathode and anode. Earlier we used carbon, so there is no reaction, but here copper is not inert. So the reaction happens at the anode. Anode, as we know, oxidation takes place. So the copper anode itself undergo oxidation. The copper metal undergoes oxidation and forms copper 2 plus ions. These ions will move into the solution. So as time goes on, you can see the copper anode getting thinner and thinner, and the copper cathode is getting thicker and thicker, because more copper will be deposited at the cathode and more copper will be moving away from the anode. So copper ions formed at the anode move towards the cathode. You can see the ions moving from the anode to the cathode. So as you can see, the blue color of copper sulfate solution does not fade in this. Earlier it was blue, now also blue. Why is it so? Because the copper ions which is discharged from the solution is being replaced from copper anode. So there is no color change, not going to be faded. The color remains blue. That is observation you can see here. That's the difference between copper electrodes and inert electrode, carbon electrode. So another application, if you can use the same process application or uses, is purification of copper, which is called refining of copper. Electrolytic refining of copper or purification. The same principle. Take the impure copper as the anode and pure copper as the cathode, and the electrolyte as copper sulfate. Same principle as I mentioned a while ago. Since anode is copper and cathode is copper, anode undergoes oxidation. So copper changes to copper 2 plus ions and moves into the solution. And already in the solution, electrolyte contains copper 2 plus ions, because we have taken the electrolyte as copper sulfate. So from the solution, copper 2 plus ions, cations, moves towards the cathode and undergoes reduction and gets deposited there as copper. So as you can see, from the anode, copper ions is moving away to the solution. From the solution, copper ions are moving to the cathode. And you will see from the impure copper, the impurities move down towards the bottom, which is being collected, and it's called as anode mud or anode sludge. Only the pure copper ions will move to the solution. The impurities settle down at the bottom. So as you can see, after some time, the anode is becoming thinner and thinner, because all the ions is being carried away to the solution and the impurities towards the bottom. And by that time, cathode becomes thicker and thicker, because the cathode is getting deposited by copper. Pure copper is deposited at the cathode by reduction. Loss of electron at the anode, oxidation. So anode is dissolved, cathode is being thickened. Next we will see the electrolysis of molten aluminium oxide. If it's aluminium oxide, you can see it's molten, so there is no ions from water, only the ions from aluminium oxide. Aluminium ion and oxide ions. So anode, what happens? Anode is made of carbon, cathode is made of carbon, so they are inert. And anode, as we know, oxidation takes place. So anions moves to anode, oxide moves to anode. And at the cathode, reduction, cations moves to cathode. Electrolyte is aluminium oxide dissolved in cryolite. Why we use cryolite is to reduce the melting point of aluminium oxide. And the molten aluminium is extracted towards this number 5. You can see, thus we will get the aluminium, molten aluminium. So this is all about the electrolysis of molten aluminium oxide. Reaction is shown there. Oxide gives oxygen gas. Aluminium Ions gives aluminium. So you get aluminium and oxygen separately if you electrolyze molten aluminium oxide. Next topic is electroplating of metals. What is electroplating? It's a process involving electrolysis where one metal is plated or coated with another one. This is done for improving the appearance and to resist the corrosion. For two things, to improve the appearance and to resist the corrosion, we electroplate metals. How it works? The negative electrode should be the object to be electroplated. That means cathode should be the object to be electroplated. Anode should be the metal you want to coat the object with. And the electrolyte should be a solution of the coating metal, such as its metal nitrate or sulfate. Example, copper plating. So as you can see in the diagram, we are going to plate a metallic spoon with copper. So the electrolyte should be a solution of copper sulfate solution. The object to be plated, such as metal spoon, is connected to the negative terminal. That means it's a cathode. A piece of copper is connected to the positive terminal. Electrolyte is copper sulfate. When the anode is made of coating material, the opposite reaction may occur, turning it into dissolved cations. For example, copper would be oxidized at the anode to copper 2+ by losing 2 electrons. In this case, rate at which the anode is dissolved will be equal to the rate at which the cathode is plated, and thus the ions in the electrolyte both are continuously replenished by the anode. The net result is the effective transfer of metal from anode to the cathode. Another example is silver plating. We are going to plate a metallic spoon with silver. So object to be plated, such as a metal spoon, is connected to the cathode negative terminal of the battery. Piece of silver is connected to the positive terminal. Electrolyte is silver nitrate. So as you can see, silver will coat on the metallic spoon. From the anode, it moves towards the cathode. The next topic is simple cell or electrochemical cell. A simple cell is a source of electrical energy. The simplest design consists of 2 electrodes made from metals of different reactivity immersed in an electrolyte and connected to an external voltmeter by wire, creating a complete circuit. The electrolyte can be acid solution, alkaline solution, salt solution, or even a fruit such as orange or lemon. So diagram is clearly given here. You can see 2 different electrodes immersed in an electrolyte, and it's connected to a voltmeter to read the voltage. This is how it works. So energy is being produced and electrical current is being produced. So example is copper sulfate solution carrying copper and magnesium. You can see copper 2+ ions are reduced to copper. Magnesium is oxidized, gives out electrons. Common example is zinc and copper. Zinc is a more reactive metal and forms ions more easily, readily releasing electrons. The electrons give the more reactive electrode a negative charge and sets up a charge difference between the electrodes. The electrons then flow around the circuit to the copper electrode, which is now the positive electrode. So you have to understand one thing here. This is an electrochemical cell. Here the anode is negative and cathode is positive. The difference in the ability of the electrodes to release electrons causes a voltage to be produced. The greater the difference, the greater the voltage produced. The electrolyte used also affects the voltage as different ions react with the electrodes in different ways. Cells produce a voltage until one of the reactants is used up. So this is an example for copper and zinc, and you will see a voltage there. Here 1.27 is a voltage. The greater the difference in reactivity, the greater the voltage. This is a cell consists of copper and magnesium. So magnesium is highly reactive metal, copper is least reactive. Difference in reactivity is larger here. So it produces a higher voltage than copper and zinc. These metals are further apart on the reactivity series than copper and zinc and produces a greater voltage. As you can see, now the voltage is 1.80. Now we can see the difference between the electrochemical cell and electrolytic cell. Electrochemical cell converts chemical energy into electrical energy. Electrolytic cell changes electrical energy to chemical energy. So as you can see, the charges of electrodes are different. Anode is negative in electrochemical cell, cathode is positive. While anode is positive and cathode is negative in an electrolytic cell. And there happens a spontaneous reaction in an electrochemical cell, where non-spontaneous reaction occurs in an electrolytic cell. And an electrochemical cell does not require any external voltage source, but electrolytic cell requires an external voltage source. As you can see in the diagram, it's mentioned here. The first one is an electrochemical cell, a voltaic cell. Second one is an electrolytic cell. So A represents an electrochemical cell where we can see energy is being produced, and anode is negative here, cathode is positive here. But always anode undergoes oxidation, cathode undergoes reduction. In electrolytic cell, also anode undergoes oxidation, but anode is connected to the positive pole of the battery, therefore it becomes positive here. Cathode is negative here in electrolytic cell. So the sign of the electrode changes, the charge of the electrode changes in both the cells. That is the difference, major difference between electrochemical cell and electrolytic cell. So I hope you understood this one. Thank you so much for watching this.